Stanford University.
Thank you for being here. And I was really proud that so many people showed up, but now I found out that it's a requirement of the course. So let me give my own recommendations. I really strongly recommend you should come to Dick Swanson's talk. And in fact, I met him here at Stanford about 30 years ago when I was working on solar cells at Exxon. And I said, finally, someone can explain solar cells to me. So I hired him as a consultant. And I would say that what I understand about solar cells I actually learned from him. And he was a former faculty member here, so this is a good reason to go talk with him. So let's talk about the subject at hand. And that is that it has to do with solar cells, and I didn't expect such a big audience. I expected more of a physics audience. So I'm going to nonetheless cover a little bit of the physics. It's not that complicated. But what makes this field very interesting, you could tell from the introductions we just heard, it's not just about physics. It's not about engineering. It's about everything. It's about sociology and economics and perception, because we have the next speaker is someone who does public opinion surveys. So that makes it rather fascinating and covers many different aspects. Now, I noticed that there are some people standing in the back, and I can assure you this talk is not good enough. It's not going to be good enough to be worth standing through the entire talk. Okay, there are spaces up here where you can safely sit, and if you really get bored, you can leave from up here just as easily from the back, and no one's going to complain. Come on, let's get some more of you comfortable here. Okay, so it's a controversial subject. It's filled with lots of crazy things. And I would not have thought that my knowledge of material science would then impact a political scandal, because now we have a political scandal about Solyndra. And I remember driving by on 880, they had this gigantic building on 880. And I said, what are they doing with that gigantic building? They don't actually have any technology. Okay, and I shook my head. And then a year later, I'm driving by, and there's a second building, and that one was paid for by the government loan. And they really didn't need that second building because they couldn't sell the stuff from the first building because they had no technology. This is crazy. But it is not very often that the scientific knowledge and information ends up being a political scandal, but this is one of the... This makes it fascinating, doesn't it? It's kind of very, very fascinating that way. Okay, so this is the topic. Okay, you see a picture of solar panels. I'm sure all of you know about that. And here is a picture, a little bit out of date, on the solar demand. It has gone up. Of course, to me, this is amazing because I left the solar field in 1984. And in 1984, this little bar was almost invisible. Maybe it was a $100 million a year business. It was a pretty small business. And I was in Germany last year, and I said, do you realize that it's going to be a 10 gigawatt per year production in 2010? They said to me, in Germany, you're out of date. In Germany alone, we're going to do 10 gigawatts. So the estimate is that last year, over 15 gigawatts of panels were installed, which is, to me, rather amazing. Because all through this period of time, the solar companies were pathetically small companies that were all losing money and couldn't possibly go public because they were just in a very poor business situation. Now, one of the advantages of having gotten into it quite a while ago is I have seen the cost drop. And the very first solar conference I attended was in San Diego in January of 1980, which is before many of you were born. And the plenary speaker was a representative of the Department of Energy, and he said, we're going to take the cost from $10 a peak watt, we're going to bring it down to less than $1 a peak watt by 1990. And I listened to him, and I said, well, what are you going to change? And he says, it's just going to be automatic, because economies of scale. And I shook my head. And sure enough, 10 years went by. It was actually a very bad period for the photovoltaic industry. No, they had not dropped to $1. They were still up above $5 a peak watt at that point. It was pretty sad. But it was just a matter of time. And so now we flash forward, instead of 10 years, we flash forward 30 years, and yes, we have achieved $1 a peak watt, or close to it. But there's another difference, is that the dollar, you might have heard, it's not what it used to be. Okay, and that's like in those 1980 dollars, it's like 33 cents a peak watt. So yes, we have achieved tremendous cost reductions, and this was not automatic. So you can go through the entire process of going from sand to silicon to solar cells, and you could pick out, okay, here this part of the process was very expensive. Oh, it got fixed by X, and this one got fixed by Y. And there were real things that they did along the way that actually made the manufacturing of the silicon solar panels more efficient, to the point that the cost has dropped, in equivalent dollars, it has dropped by a factor 30, which is very, very impressive. And in a way, not surprising, because it's like any other industrial process. There are so many inefficiencies and problems and bottlenecks. And if you solve those things and you actually fix them, you can actually make a huge difference in cost. And it brings us to the idea that the solar panel doesn't really have to cost very much at all. And it could be a very, very thin layer of material, and would end up having a cost even much lower than the cost we're looking at today. In fact, if we extrapolate the same rate of cost reduction, a factor of 30 over 30 years, if you do logarithms very quickly in your head, that's a factor of 3 every 10 years. It's not a huge factor, but it's still a real drop in cost, factor 3. So as people project over the next 10 years, another factor of 3, why not? Because we've had 3 decades, each one with a factor of 3, so another factor of 3, so that by 2020, it's going to be even 1/3 the cost it is today, and it is believed that by 2016, that subsidies will no longer be needed, that the industry will be going so fast in the non-subsidized markets that the subsidies will be kind of irrelevant. And some projection, a little bit controversial maybe, that even as we have 40 gigawatts installed today, but heavily subsidized, but still 40 gigawatts installed is mind-boggling. It's a huge amount. That people are projecting in 2020 to have a terawatt of installed capacity, which is truly a very large number. So it has grown and changed tremendously. The cost reductions are very tangible. Now I'm going to embark here on part of the social controversy, and it's also a business controversy. And the business controversy is, should I be aiming towards solar cells that have a very low cost, or should I be aiming towards solar cells that have a very high efficiency? I can't believe that 30 years after I got into this field, this battle is still being fought, okay? And I say should not have been a battle, because if you look at the cost of electricity, and this graph came from Professor Barnett of the University of Delaware, is that the efficiency is in the denominator of all your other costs. And so naturally, the lower the efficiency, the higher the costs, okay? And those people who say, well, it's true, I have a very low efficiency, but my cost is very low. And that doesn't make any sense. Okay, and it certainly doesn't make any sense in the long run. And if you just accept this simple cost equation, it ends up, of course, the highest efficiency ends up having the lowest cost. And that, I would claim, is inevitable. But there are many people who disagree with me. For example, there are many researchers who continue to work on very low efficiency technologies. There are also many, let's say, venture capitalists who fund, and the government, who fund approaches that don't seem to have any prayer of ever going to high efficiency. And so there's obviously a very big difference of opinion. So I don't want to blame the government, because here's Wall Street. And so I'm going to give the tale of 2 companies. This is First Solar, a respected company that has perfected the cadmium telluride thin film. Okay, and well, it doesn't have much efficiency potential. They talk it up a lot, but they're basically at 11% efficiency, and they're to be congratulated for reaching 11% efficiency. And the market capitalization, well, this is a little out of date because the market has gone down a lot, but it was close to $10 billion when I took the screen capture. Now, this is to be contrasted with another company, SunPower, which was founded by your own Professor Dick Swanson, who is probably the smartest guy in the whole field and has been there the longest and so on, has done something very clever that he has raised the crystalline silicon solar cells to 23% efficiency, not in theory, but in the manufacturing plant. Yet the market capitalization for SunPower is much lower, only $1.7 billion. Okay, so obviously this is not an academic question. This is a dollars and cents question. If you were someone who really believes me very strongly, don't be careful. Don't go out and sell short. You could sell short on First Solar and go long on SunPower because you see the imbalance. Of course, both are very dangerous investments. So don't consult your own advisor. Okay. Okay, but it shows that there is a difference of opinion. Is that some people think efficiency does not matter, to which I'm shocked. But it's all of Wall Street. So who might argue against all of Wall Street? So it's very, very puzzling and controversial. Obviously, there's a difference of opinion, and you can vote with your own money if you want to. Okay, so I'm going to, this has been sort of the social introduction. Then I'm going to have a scientific section where I talk about achieving very high performance in solar cells and achieving it at low cost. And toward the end, I talk about how the costs are coming down and what we should be doing next. Okay, so please bear with me. The next umpteen slides are the science of the solar cell. And so I have here a bunch of questions. For example, why is the p-n junction necessary in a solar cell? Some people think so. I don't. I say it's optional. What determines the voltage of a solar cell? That isn't discussed very much. Everyone seems to know how to determine the current, but the voltage, they don't seem to say much about that. But it's just as important, if not more so, than the current. And then one of the things, like any energy machine, it's all about statistical mechanics and thermodynamics, and that has a big effect on the optics, so I'll talk about that. And then because I am sort of the originator of photonic crystals, people ask me, are photonic crystals of any help in solar cells? It's kind of an interesting question. And then what are the top competing technologies, et cetera? Okay, so first of all, I have to describe what is a solar cell. And think of a solar cell as a container, and it captures photons, so the photons come in, and it produces electrons and holes. And what it does, it simply tries to contain the electrons and holes and to build up a very, very high density of electrons and holes. And now, so you want to prevent them from recombining. So you coat the surface of the container. Let's say the container is silicon. You coat the surface with silicon dioxide, which has a bigger band gap. And so as the electrons and holes strike the surface, they're repelled by the larger band gap of the silicon. And then so what makes it a solar cell? So you make a contact, and metallurgically we know how to do this. We can make an electrical contact that only allows holes to pass. So the holes will pass through. And we can make another contact that only allows the electrons to pass, and the electrons will pass through. And if you are well-versed enough in physics to talk about Fermi levels, the electron gas and the hole gas are quite independent. They each has their own Fermi level, and so you'll be getting electricity at two different potentials, and that will be the output voltage of the solar cell. And of course, you'll collect the current according to the number of photons that came in. Notice that there is no p-n junction. Okay. Now, often people ask, well, how does the electron know to go to the electron contact? Okay, well, it kind of diffuses around, random walks, and it diffuses toward the electron contact and say, aha, you need to have a built-in potential. Okay, and no, you don't really need a built-in potential, because if you calculate the diffusion gradient required to drive the electrons to the contact, it's very small. Maybe you'll lose a millivolt driving the electrons to the contact. So I suggest maybe disabusing yourself of the idea of a requirement. You can have a p-n junction, we often do, but it's not absolutely required. Now, what about the selective contact? Hey, how easy is that? Well, we have a way of doing that. There are, in semiconductors, there are ways of making semiconductors with two different band gaps, and you could arrange the potential such that the electrons will flow directly out, whereas the holes would be blocked. And so this is a contact for electrons, and likewise the electrons could be blocked, and the holes could go straight through. And so that's it. That's all it takes to make a solar cell. Now, let me give you a kind of a hydraulic model. Often in physics we come up with models, in this case with rainfall. So think of the sunlight as being like rainfall. It's falling into the bucket, and you're trying to build up a very high pressure head here in the bucket. Okay, and but you're fighting certain tendencies. The leakage of the droplets out the bottom of the bucket, that could be called bulk recombination. And a leakage of the electrons and holes out the side, that could be called surface recombination. Okay, and at the same time, you have a faucet, and it's driving a flow of water, which is driving a water wheel round, and that's where you get the useful workout. And but you see right away there's a bit of an issue, is that if you let too much water go into the faucet, you'll have no pressure head. But if you try to get the highest pressure head, maybe you won't have hardly any water. So let's talk about that. Okay, so here are three possible valve conditions. And you could have a tremendous flow, but there's no pressure, so the water wheel barely turns. Or you could have a very tiny flow, but you built up a tremendous pressure because you didn't let the water escape, and then the water wheel doesn't turn at all. Or you could sort of have a balance between the two. And in solar cells, this balance is very, very important. We have to have not too much water, not too little, and then we get the maximum power output. And this is very similar to a solar cell, where we have the IV curve of a solar cell, and this would give you the maximum current, and this would give you the maximum voltage, and in practice you have to compromise. And so there's this concept in solar cells called fill factor. So this is the current times voltage is this rectangle, and it gets divided by the area of the fantasy rectangle. The fantasy rectangle, if you could simultaneously get the maximum current and the maximum voltage, of course you can't. And that ratio of the area of the two rectangles is called a fill factor. And actually we are now making solar cells where the fill factor is pretty close to 89%. So that's pretty good. But it's sort of unavoidable. You can never have everything at once. And so this is just a recognition of that. And it's also a recognition of thermodynamics, which I'll try to indicate a little bit later. Okay, so that is the fill factor of a solar cell. Now, the next question about the solar cell is how much current to expect. Obviously, you want to absorb all the incoming light, and you want it in as thin absorber as possible. Why? Because you're paying money for the absorber, and so you'd rather use less of it. Okay, and so it's kind of self-evident that a stronger absorber is better than a weaker absorber, and this pushes you toward direct band-gap solar cells like gallium arsenide, although you can often do reasonably well with indirect band-gap solar cells, but they have to be a lot thicker, like silicon. So this would be gallium arsenide, and that would be silicon. Okay, and it has to do with the thickness. So let me just say on this point is that, yes, gallium arsenide is more expensive than silicon, but it absorbs 10,000 times more strongly, okay? And it is not 10,000 times more expensive. So now there's the first paradox. The more expensive material is actually cheaper, okay? Just like everything else, when you analyze it correctly, there's often a paradox, especially in economics, business, politics, the hidden side effects, etc. So that's something to ponder. Okay, now I'm going to describe a simple to explain physics thing in solar cells. And that is, suppose you have a flat solar cell like this, like most of them used to be, and the photons come in, and well, you're supposed to have taken your freshman physics class, so you get refraction of light toward the normal, and then it goes out again. And it's a single pass only. Let me contrast that with the situation when you've made the surface rough. And if you make the surface rough, what's going to happen? Yes, you could get some refraction going in, but there's some funny angle. It scatters off at some funny angle, and before you know it, it doesn't remember the original angle, and it scatters again, and before you know it, it has a devil of a time trying to escape, because this escape cone, this is the cone over which light is able to escape, is very, very narrow in the case of semiconductors. And let me illustrate it here by comparing the solar cell with the light-emitting diode. So this escape cone is just part of normal optics. If you're a diver, you know that at a certain angle under the water, you see the reflection of the sand. You can't see out. And this is a very severe problem in semiconductors because the refractive index is 3.5. And so this angle, this particular angle, is only about 16 degrees. And so only a tiny amount of the light is able to escape. And let me show you the same problem in a light-emitting diode. So the light-emitting diode is the inverse of the solar cell. In a light-emitting diode, you're trying to get the light to escape, but only the light in the escape cone. So if you figure out, okay, oh, it's only 16 degrees, what percentage of all the outgoing light is that? That's only about 2% of the light. And that's where that 4n squared factor comes in. And if you're going larger than 16 degrees, whoops, oh, you totally turn and reflect it, totally again, and so forth, and you get trapped. And they used to, believe it or not, they used to make light-emitting diodes this way. They didn't take this into account. So, well, there's a solution for solar cells. I said you make the surface rough, and then the internal path length becomes much longer because it bounces around so much. And it's actually 50 times. This 4n squared factor is 50. Because index 3.5 squared is 12 times 4 is about 48. It's actually 50. Okay, so it's a tremendous increase in path length. So let me say, well, what implication does that have? That says that you can get by with 50 times less of the expensive material that you thought you would need. That's actually huge. So this is a huge, huge effect in terms of cost. You can trade it off, you get more current, obviously, and much less obviously, you actually get more voltage when you do this. So it's all kind of amazing. They do the same thing in LEDs. They make them rough so that most of the light does not get trapped. And so there's a huge attention now in LEDs. After 50 years of LEDs, they are finally putting a huge amount of attention in how to make it rough in exactly the right way. So yes, the light is trapped, but eventually it is able to escape. And for this reason, the old LEDs used to be 2% efficient. Now we have LEDs that are 50, 60, and 70% efficient in some cases. So that's kind of remarkable. So this has to do with the shape. You know, certain shapes trap light and certain shapes don't. And so this slide has to do with stuff you learned when you were in kindergarten. You learned about the blocks, the shapes. We all learn about shapes in kindergarten. But they are very different. The shapes are very different depending upon what they actually are. And so when I was in graduate school, I took a course on statistical mechanics, and the professor said some things are ergodic and some things are non-ergodic. And I finished the class, and I said, phew, I finished that class. I'm probably never going to have to use the word ergodic again. Okay? And so what does it mean? It means that the time average is the same as the average over what's called phase space in physics. Phase space is just all the physical possibilities. So the time average explores all the different physical possibilities. Well, let's look at the sphere. It does not explore all the physical possibilities at all. And so the time average is not the average of every physical possibilities, because any light ray that could have gotten in can also get out. And the same with the rectangle, and the same with the parallelogram. So these are non-ergodic shapes. Okay, but now you're in kindergarten, so now you learn about the ergodic shapes. The oval. Well, the oval is different enough from the sphere that the oval allows light to be trapped. And once it's trapped, you get this very big factor, this 4n squared factor. The trapezoid likewise. So here there's a dashed red line here, and the reason for the dashed red, these are two different worlds. And although we're talking in terms of kindergarten shapes, we're nonetheless talking about subtle concepts in physics and in mathematics. So something is ergodic versus something is non-ergodic. Whoa, talk about going from kindergarten all the way to graduate school in theoretical physics. Whoa. So nonetheless, this is where we are, and we'd rather make solar cells of this type than of that type. And the difference is rather huge. And I can give you one example but maybe you haven't had this personal experience because you're not old enough. In the old days, people used to smoke cigarettes. And there were the glasses, so that you would have ashtrays. And the ashtrays were invariably very artistic. And some of them were made of glass. And obviously, they had a very complicated shape. Okay? And so I want you to visualize this artistic sculptured piece of glass. And you take it out to the parking lot. And the other thing you take out is a glass window. And you put them out in the parking lot. So, well, there's one sun. Obviously, there's just one sun in both of them. It's not quite true. Because of the odd shape of the glass ashtray, it's going to have a tremendous amount of internal sunlight bouncing around. It's going to have 4n squared, which n squared, okay, 1.5 squared is 2.25 glass, 8 times. You could have 8 suns. You've done nothing. It's totally passive. It's just a sculptured piece of glass versus a flat piece of glass. And in the sculptured one, you have 8 suns. And in the glass window, you just have 1 sun. So that is like a huge difference, that there's actually 8 suns bouncing around in there. It's very thought-provoking. So we've got to obviously take advantage of this. We need a few other ways to look at it. So this is one way to look at it in terms of statistical mechanics. Well, if you've gone through, graduate school in physics, then you know the density of optical modes has n squared in it. So that says that there are more places to put light. There's n squared times greater places to put light. But you pick up a factor of 2 from double pass and a factor of 2 less obviously from cosine theta averaging. And so the net benefit is 4n squared. So that's why it's 4n squared and not just n squared. And so this is the benefit. And by the way, virtually all solar panels made in the world today, which is, let's say, a good fraction of the 15 gigawatts that were made last year, they all have this texturing. They all take advantage of this. Not to the maximum degree, but still they take advantage of it. So you can have, in principle, 50 times thinner layer. And a thinner layer, the carriers don't have to go as far, so there could be less series resistance. But even more importantly, the operating point voltage goes up. And this is a little bit subtle. And it goes up by kT natural log of 4n squared. I'll show you where that comes from later. That's a lot. A tenth of a volt at the operating point is a huge improvement. Now, but then people ask me, you want total internal reflection? That's going to be defeated by the anti-reflection coating, because every solar cell should also have an anti-reflection coating. So it's just part of the English language. It's a mistake that the English language tries to trick us, is the anti-reflection coating is actually totally compatible with total internal reflection. And the reason is that the anti-reflection coating only has to do with the light rays inside the escape cone. And for all the other light rays, they would have been trapped regardless. And so those two things are quite compatible. Now, so people ask me, can a photonic crystal do better than a random rough surface? So a long time ago, I proved that if you're in the world of geometrical optics, and it's not much different, the proof was not much more than what I just showed you. In the world of geometrical optics, a randomly rough surface is already reaching this statistical mechanical limit. So there's no point trying to do better than a randomly rough surface. But we are now approaching the situation where I keep saying about how a thin solar cell is a cheaper solar cell. Well, I'm going to show you that now the record-breaking cell is about a micron thick. Someday soon, the record-breaking cell will be a tenth of a micron thick. It costs 10 times less to make. And then it's going to matter, because how do you texture that? And so there will be some kind of texture. It most likely will be a photonic crystal. But although there's a lot of research going on this, and I know Professor Shanhui Fan here at Stanford is doing a lot of research on this, it's a race now. There's work at MIT, and we're trying to do some work. So no one knows what the best surface texture should be in the case of wave optics, when your film is thinner than electromagnetic wave. Okay, so that's all I wanted to say about the current. And now I'd like to go on to the voltage. So we've done fill factor, we've done current. Once we do voltage, that's everything you need to know. However, voltage is much more subtle than current. Current, you say you want every photon to give you an electron-hole pair. What about the voltage? Where does that come from? So There is a worry that people have is that what if the electrons and holes don't want to go into the wire? Okay, and they're happy where they are. They're sitting in this container, the semiconductor container. It's like a bucket. So you have to give them a reason to go into the wire. And so the reason we give them is we say, well, we're going to lower the voltage. And indeed, when you operate a solar cell, you have to lower the voltage below the open circuit point. So the open circuit point is if you draw no current. And if we give up a few kT, and it's this little quantity here, it's around 4. We give up a 4 kT, 98% of the current, and this is actually the optimum situation in solar cells and in all types of solar energy, even photosynthesis. Even in photosynthesis, you could say it's working well when 98% of the photons are used and 2% are given away or thrown away. They're not really thrown away. It's required by thermodynamics. You cannot have, in thermodynamics, entropy says you cannot have 100% of one thing and 0% of another thing. In thermodynamics, there's always a balance. And the balance in solar cells is you collect 98% of the current. That's the good spot, the maximum power point. And then 2% ideally would just be radiated away. It's not a loss. It's just part of thermodynamics. You can't waste that. But the main point of this slide I wanted to give you is there's never a problem. You can always extract the current. Okay. But the important thing is you're going to lose a few kT. In doing so, focus on the open circuit voltage. And so let's talk about what is the open circuit voltage to expect. And so everybody, even a freshman in chemistry, learns about the Boltzmann factor. So I'm going to use the Boltzmann factor. And the Boltzmann factor looks something like this. There's a free energy over kT. So, and then there's a ratio of probabilities. So this ratio, the probability of being in the excited state, when the sun is shining, yeah, there's a big probability of being in the excited state. But even in the dark, the probability is not 0. So it's the ratio of these two probabilities is exactly what the Boltzmann factor is. It's just a ratio of populations. Okay, now you can invert this formula. It has an exponential, so I can take a natural log. I convert this formula completely, and I could solve for the free energy. I solve for the free energy. It's now kT log of this population ratio. And that's kind of interesting. And this is actually the correct formula for molecules. However, I was very surprised. So I did the formula, and you could look it up. You can look it up in the books. It's the same formula for solar cells, and there's a 2 in here. It's kind of fascinating where this 2 came from. And let's see, I'll have to save this story, but it's a very interesting story having to do with Bob Schrieffer explaining this factor 2 to me, but I'll have to skip that. Okay, so let's say it has to do with the population ratio, and the population ratio has to do with the how hard you're pumping. So you could actually convert that into the pump rate actually ends up as external emission, and then you still have the band-to-band emission in the dark. So this becomes then the formula. And this is the formula worked out by Shockley. And a fantastic formula, poorly understood, and it is simply the Boltzmann factor with the ratio of populations, and the upper population is represented by the pumping by the incoming sunlight. And so this tells you the voltage to expect. Notice it has kT, and I'd like to derive it in a slightly different way, okay? And that is to invoke entropy of photons. So yes, photons do have entropy. That is often neglected. Now, if you go far enough in this, and nobody learns thermodynamics anymore except material scientists, but I'm going to tell you that there's a formula that you get. The photon energy, the free energy, I want to know the free energy. So that's a correction. You start with the photon energy and you subtract off something to do with the entropy. And obviously, if you have a lot of entropy, that's bad. And so it means that's not as useful a form of energy. And so what could possibly be the entropy of a photon? And I'll tell you in a minute because it's really easy to understand the entropy. But I can give you a formula from statistical mechanics. Entropy is K log W, number of configurations. And so now the entropy of a photon, this, by the way, applies, you go out into the parking lot, go out of the building. Yes, it is meaningful to ask, what is the energy of a photon? Everybody knows Planck's at h nu. Less obviously, what is the free energy of the photon? Oops, you mean the photon has entropy? How much is it? So I'm going to show you how to calculate it. So this is the operating point voltage is equal to all of these things. And each of them is in the form, usual statistical mechanical form, kT times some numerical factor. So let's talk about this first one. First, you start with the band gap of the semiconductor. That's the most voltage you could get. Okay, but then those are the photons right at the band gap. Then you have to start subtracting entropy. And so, well, what is this funny term? Oh, this solid angle, this is the solid angle subtended by the sun. And what's going on there? So somebody would say, wait a minute, this is solid state physics. What does it have to do with the solar system? This is solid state physics. Yes, but we do something funny with sunlight. And what it is, it's kind of a smart thing to do. We kind of know the sun is up at a certain angle, and it subtends a certain, maybe a small solid angle. But then that's useful information. We could use that maybe to get more energy out of the solar cell and more voltage, certainly. Then we throw that information away. Say, no, we want a solar cell that accepts light from every possible angle of the sky, because the rest of the sky is filled with light. Now, one of the important things that nobody tells you is how much of the light is, on average, coming directly from the sun and how much is coming from the rest of the sky. So I'll tell you this number. In the climate, it depends on climate. So in the Stanford climate, 70% of the sunlight is coming directly from the sun and 30% is coming from other parts of the sky. We cannot afford to throw away 30% of the sunlight. So when we design our solar cells, we make sure that they accept the light from every possible angle. So we have thrown away the information of where the sunlight was actually coming from. We've tossed that away. That means there's some entropy. We had information, we got rid of it. How many different combinations? Well, it's the small solid angle subtended by the sun, and we're dividing by pi steradians. Pi steradians is all the other angles in a half space. Work out to be pi steradians. And so that number is like 50,000 or so, or 25,000, it's a big number. And that is the biggest number of different configurations the photons have. And that is your biggest entropy. Throwing away the information of the directivity of sunlight is your biggest entropy. And that is the main reason why we don't get a voltage corresponding to the band gap. Immediately from this kT, natural log, it's roughly, it's like, 30,000. Natural log of that ends up being close to 12. And so we lose, let's say, 11, 12 kT. So we lose 280 millivolts immediately, okay? Let me put some other factors in. If you trap light, that also has an effect because the angle subtended by the sun is even narrower. So if you don't use the light trapping, you lose an additional kT log of 4n squared. There's another tenth of a volt. Then we lose another tenth of a volt, kT log of this number, and this has to do with giving the carriers a reason to go into the wire. So we lose another tenth of a volt, and then we can lose a huge amount if the material is not very good. There's effectively a lot of uncertainty and disorder if the material doesn't luminesce well, as you could lose anywhere from 0 to 0.3 volts that way. And some solar cells that are highly touted lose the additional 0.3 volts. And then there's some minor corrections, which I won't get into. And by the way, so where did this treatment come from? This is a very beautiful way to derive the voltage of a solar cell. And this was actually derived by a student at Berkeley, Mr. Ross. This was a long time ago. This was 40 years ago. And he was a student of Melvin Calvin. And Melvin Calvin won Nobel Prize for explaining photosynthesis, and he told the student, figure out what's going on with the thermodynamics. And he was inspired by Shockley's treatment, and then he generalized Shockley's treatment this way. So it's kind of a nice way, and it does something you're not going to see in your other classes. It assigns entropy to sunlight. and which I think is perfectly reasonable, and every educated person should know how much entropy there is in sunlight. And so this version, this way of deriving it, is from an old paper by that student. Okay, so now I have to make a comment that is sort of executive decision makers in the audience. Let's say you have funding and you want to decide, do I give it to a material that has a big band gap, or do I give it to a material that has a small band gap? Because both of them could be reasonable solar cells. So let me show you what the problem is. If you start with 1.1 volts, which is the band gap of silicon, and now if you add up all the terms on the previous slide, you're losing 0.8 of a volt. So by the time you're at your operating point, you've only got 0.3 volts output. That's from all those big photons. You had 2-volt photons, you had 3-volt photons, and all you end up with is a lousy 0.3 volts. Now, if the band gap started smaller than 1.1 volts, then you could end up with nothing. Okay? And so this is a very strong statement that if you have an incredibly clever idea, and just to mention hot carriers to produce more electron-hole pairs, in order to produce more electron-hole pairs, you have to have a small band gap. If you have a small band gap, you run into this problem with entropy. Those infrared photons, those small band gaps, don't have enough free energy to be worth the struggle. And unfortunately, the decision makers are not always aware of the thermodynamics, even the scientists. Okay, so the title had high efficiency. So let me get into the high efficiency now. 25% has existed for many years. And now we're jumping up close to the theoretical limit. So the theoretical limit that Shockley laid out is 33.5%. And we've been stuck at 25. Now, in order to get closer to the theoretical limit, some new physics is needed, and I will tell you what the new physics is now. Okay, and that now we're up here, and I'm going to try to indicate why we're up there. So, of course, you have to respect Shockley. So what did he say? He said that for every, ideally, this is the ideal world, for every photon, solar photon coming in the ideal world at open circuit, at open circuit, there's no current, so the electrons and holes have no place to go. Shockley says therefore they have to go into outgoing luminescence, and that would be the ideal situation. Every incoming solar photon gets converted to outgoing luminescence, and then you get your highest open circuit voltage. Another way of saying it is you have the minimum loss mechanism. You cannot dismiss luminescence. It's not a loss mechanism because it is imposed upon you by the laws of thermodynamics, the laws of radiation. If you can absorb, you must emit. Okay, and so the luminescence is inherent and unavoidable and not a loss mechanism. However, in trying to achieve what Shockley wants us to do, which is to get all the light coming back at you, coming back at the sun, we have a problem. The escape cone is only 2%, and 98% of the light is trapped internally. This is very bad. And indeed, what Shockley said is this. You have your ideal open circuit voltage, and then you're going to lose voltage according to your external fluorescence. Very counterintuitive, because you'd think all that light coming back at you, that's wasted energy that you could have used. And nonetheless, it's counterintuitive, but you actually do want to have that light coming back at you, because that allows you to have the highest open circuit voltage. So you want your external efficiency to be 100%. This would be log of 1 is 0. You lose nothing, and you get the maximum ideal voltage that Shockley decreed. So what is this new physics? This new physics is represented here on this slide. This is the physics of the solar cells that are below 25% efficiency. Maybe you've seen this in books. This is normal. The photons come in, they get absorbed, and you collect the electron and hole pair. They go in opposite directions, they get collected. Okay, the new solar cells at above 25% are very different. Of course, the photons come in, the green photons come in, they get absorbed, etc. But you also have, accompanying this, a tremendous amount of fluorescence. And it has to be very, very high because only 2% of it is able to escape. So these new gap, this is band edge luminescence or fluorescence. And what it says is that the new physics is shown in part B here, that yes, you have your incoming photons get absorbed, but accompanying that, inside the solar cell, there should be a tremendous photon gas representing as much as 50 suns of internal fluorescence trapped and some of it escaping. So that represents the physical situation. Unless you've done that, you're not going to get close to the theoretical limit. You won't get past the 25%. And it's very counterintuitive because normally we think, oh, fluorescent photons, that's a waste, that's a loss, but it's not. It is exactly what you need to get the highest efficiency. In fact, that fluorescence is kind of like a measure of the internal voltage. Well, now, why is this a vexing problem? Well, because you're going to bounce around many, many times. You might even get absorbed, re-emitted, and so forth. You might need an internal efficiency of 99%, even to have a 50% chance of getting out. And so this puts a tremendous burden on the internal efficiency of the material. And this is why nobody has really broken the 25% barrier until now. Now, here's a way to look at this. You get reabsorbed. The recycled photons are not lost. They are reabsorbed. Effectively, you recreate the electron-hole pair. Therefore, the carrier lifetime, you haven't really lost the electron-hole pair. The effective lifetime increases. That increases the carrier density, and that increases the open circuit voltage. It's one way to look at it. But it's hard to do. It's hard to get 99% internal fluorescent efficiency. It means you have to have a very wonderful material that fluoresces so well. And indeed, the benefit occurs mostly above 95%. So this is an example. If you have internal fluorescence yield, how much does the efficiency go up? Well, here's 90%. It's okay. But the real steep region of the improvement is actually above 95%. So it really puts a very heavy burden. Likewise here, the real improvement is above 95%. And you have to have usually a reflector to avoid losing the photons. Again, a reflectivity well above 95% because most of the benefit occurs up here, above 95%. So that's quite a severe challenge. Now, how to think about this? I guess this is sort of the main point I wanted to show here was that if you go from 100% internal fluorescence yield to 90% to 80%, almost all of the penalty is between 100% and 90%. And going from 90 to 80, the penalty is rather small. Okay? But there is sort of there's a second purpose in this graph. Remember, I was disrespecting the small bandgap solar cells. And notice the small bandgap solar cells, well, it looks like they might be pretty good down here, but notice how vulnerable they are. So here, you have a tremendous loss in performance if you don't have 100% internal fluorescence yield. Whereas the big bandgaps, you have a loss, but it's not very significant. So there are some ideas out there for using the small bandgap solar cells. They lack robustness because if somehow you have to compromise and you don't have well over 90% internal fluorescence yield, they perform badly very quickly. So another little editorial. So where did this come from? Well, this all came from the voltage increase. You're looking, where did the efficiency come from? Between 90% and 100%, you have a very substantial voltage increase. So this is actually quite significant. And so here are some calculations of what to expect. And I'd like to contrast what's going on here between two situations. This is the situation if you have a good mirror, let's say 100% mirror, versus a bad mirror, a 0% mirror. And notice the difference in the open circuit voltage. So the mirror quality, surprisingly, has a tremendous effect on the open circuit voltage. So let me tell you where the world of technology is. This is the record that existed between 1990 and 2007. This is for single junction flat panel solar cells and was pretty stable for 17 years, about 25.1. As of last year, it had jumped to 26.4, but still not that great. And so you see there's still a big discrepancy. What can fill that in. Okay, so we jump ahead 12 months from June of last year to June of this year. And the Alta devices, of which I'm a co-founder with Professor Atwater from Caltech, jump that over 2%. They're actually already at 28.3. So it's rather a big jump. And from the record a couple of years ago, it's like 3% boost. But in 12 months, they raised the voltage. The record cell went from 1.03 volts to 1.11 volts. Now, we presented this at the photovoltaic conference in Seattle in June. And we had our Alta guy, he's a young student, just 2 years out of his PhD, and he's presenting this. And the first question in the audience, maybe this is quantum well with a bigger band gap, because they can't believe the voltage, because this is 8% improvement in voltage in a 12-month period. So I said, this must have been a really thin quantum well. I said, no, it's a micron thick. Next question, is this really gallium arsenide? These are the questions from the audience. Okay, is this really gallium arsenide? So it is a kind of, it defies people's intuition, or it just defies experience. The record was this, and in 12 months it jumped by 8%. And it all has to do with the new physics I talked about. Do you have good fluorescence? And is the fluorescence bouncing around inside? And are you getting the fluorescence out? And that's the new physics. And it entirely impacted the voltage from that formula from Shockley. Remember, it's the ideal minus KT log of the extraction efficiency of fluorescence. Even at the 1.11 volts, that translates to maybe only 10% extraction. So there's a lot of room, and the theoretical limit is more like 1.15. And actually, Alta is headed there. So what can reasonably be projected? I think no one's going to argue if you're at 28.3 that you might be able to get to 30. Okay, so I think we are facing the future world is that 30% will be a normal solar cell efficiency, single junction flat plate, the simplest possible combination. And so that's something that certainly has I think it's good, it's tremendous for solar cells to be looking at the 30% efficiency, but you have to incorporate this new optoelectronics in there. And I don't want to dwell on it, but it's all about extraction. This is comparing the good mirror to the bad mirror. Good mirror, you gain 3% efficiency, and what is the net effect here? The good mirror, you have 79 or 790 microamps of external emission, versus the bad mirror, you have 40 microamps. It's all about getting the light out. The light out actually is the voltage. It translates. Thermodynamically, you can show. The light out is translatable directly to the voltage in. And so that's why we have to get the light out. So this was contrasting the old cells with the new cells. And here, once they're bouncing around inside, you have a chance of getting them out. Okay, so what are the technical conclusions? Is that if you really want to have the highest possible efficiency, you need to have tremendous external emission, very counterintuitive. However, it does demand very, very high internal fluorescence efficiency and very high internal reflectivity, well over 90%. And if you want to look at it my way, I say, well, why? What's counterintuitive? So think of the external luminescence. It's actually a voltmeter into the solar cell. You better have external luminescence, or you're not getting the voltage that you have a right to expect. And stop worrying about the electron hole transport. Stop worrying about those things. Worry about the photon management, the photon transport. Because once you've reached 25%, the electrons and holes are doing fine. If you want to go above 25% efficiency, it's all about the photon management. And so that says a good solar cell should be a good LED, and that the solar cell performs best when there's maximum external fluorescence. Okay, and this is explained in, we have a preprint online. Okay? And there's some ideas. So people ask me, well, what research should we do now? So I claim that we should be researching efficiencies above 30%, because that's going to be available in a plain vanilla single junction solar cell shortly. And so we need to think about multi-junction cells. There are a number of ways of doing that, even based upon the gallium arsenide that I showed you. You can have a wider band gap. So there's a material that is a very nice material that matches the gallium arsenide, can be grown together, and will give you the dual junction effect. So you have two different junctions. And there's even some tricks you can play. You can use the luminescence from one to be absorbed in the other. There are a lot of tricks you can play. And you can even play these tricks with quantum dots and so forth. But whatever you do, please don't research any more 10% efficient solar cells. I say, yes, take that 10% and make sure you're adding it to the 30% we already have. So you should be researching 40% efficient solar cells. And this is another way to do it. The point about this slide is just if you go through the mechanics of a dual junction, this is a dual junction solar cell, you can make a lot of mistakes in the upper junction. Even not absorbing photons, as long as the lower junction is performing well, you're still okay. If you have a creative idea, it's likely to end up in the upper junction of a dual junction solar cell, where we have a lot of latitude for forgiveness for wild ideas. And where, let's say you don't absorb the light, no problem. It goes through and gets absorbed by the lower band gap, so it's still okay. However, people talk to, I'm back to cost now, and we're back to sociology. So obviously gallium arsenide are the preferred solar cell where cost is no object. So we have a bad reputation in gallium arsenide. You must be the high cost technology, therefore I shouldn't be listening to you because it's all high cost. But it's not true. And this is some recent publicity from Alta Devices, and where they raised a lot of money, but they were keeping secret until about March. But I can tell you a lot more about what Alta is doing now. We've had several press releases since March. And one of the things they're doing to make the gallium arsenide very cheap is called the epitaxial liftoff process, which is a remarkable thing, which was discovered 35 years ago. People credit me with it, but there are people who actually did it before me in Japan. And there's an American guy who says he gave the Japanese the idea, but basically it takes advantage of something that's very common in nature, is selectivity of solution. So some things are soluble, some things are insoluble. If you have 40% aluminum, or let's say just aluminum arsenide, which is what we really use, acid can come in. It'll only attack the aluminum arsenide. It will do nothing to the other alloys. So at 40% aluminum, let me say it this way. At 39% aluminum, it is not attacked by the acid. And at 41% aluminum, it is attacked in the alloy. And by what I mean yes and no attack, there's 8 orders of magnitude in selectivity over a very narrow percentage range of composition. So what this means is you can come in very large distances and just float off these epi layers, and then you can reuse the substrate. The beauty of this, you only pay for the semiconductor you use. And the gallium arsenide, it's already a micron thin, and it isn't even using light trapping, so eventually it's going to be maybe a tenth of a micron thin. Please trust me, the cost is almost negligible, even though it's expensive stuff. Okay, now, and the liftoff process, I can't show you how Alta does it, but in the literature there are some examples. And so here's an example. You come in with a droplet of hydrofluoric acid. It just undercuts it, and it's very, very fast. And, oh, I actually have one in my briefcase, if I can just remember where I put my briefcase. Okay, so this example from literature is 2 inches in diameter. Let me show you what is actually being produced. Okay, so this is a single crystal epitaxial gallium arsenide film capable of breaking world records. It is inorganic. It is nonetheless very flexible, as you can see. The size, you can't tell the size from the back, but on the diagonal it's 6 inches, so it's a 100 millimeter by 100 millimeter square. And we think we can produce these things at almost no cost. And we think, well, we know that we've proven all these efficiencies that I quoted were verified by a National Renewable Energy Lab. Okay, so I think the cost is getting out of there. I mean, it's just going away. And that we are going to be in a world, let's say 10 years from now, where solar panels are very, very cheap, even compared to the subsidized Chinese solar panels of today. That in the future, they will be much, much cheaper. And the overall system cost, of course, the efficiency matters a lot. So tremendous improvements expected there. So you might say that I'm trumpeting my own company. But this idea of peeling the films off the surface has legs. And I'll give you an example from the silicon industry. And this is some work from IBM. They are now peeling silicon. So we're peeling gallium arsenide. We're very worried that they're able to peel silicon now. Okay? And the peeling, it's kind of tricky. This is nickel. This layer is nickel. And it's electroplated, so it's under compression. And when you yank it off, it cracks, and a crack starts. But the part of the silicon that's very close to the nickel is protected by the compression of the nickel. So something under compression doesn't crack. And you end up, in a controlled way, peeling off a film approximately 20 to 50 microns thick, which is exactly the right thickness for a silicon solar cell. So this is really pretty amazing. And of course, this completely knocks the costs out of silicon. I mean, whatever the Chinese subsidy is now, it's kind of irrelevant because this will greatly, greatly reduce the cost of the silicon. And this is, it's not just IBM. This is a startup in Austin, Texas called Astrowatt. They're doing the same thing. This is sort of an example. Like I showed you, peeled gallium arsenide. This is peeled silicon. So now you have two different ways of completely reducing the cost of the semiconductors, that the solar cells are going to go way down in cost. The efficiency will be very high. Of course, I got very worried. I called my CEO, what are we going to do about these silicon guys? They're starting to peel now too. And he says, we still have the efficiency advantage, okay? Because it's quite significant. We're going to be close to 30%. Maybe the silicon will be maybe in the low 20s. But we haven't put on our second junction yet. So we could very easily, as I showed you earlier, we could very easily make a dual junction cell that gets us into the 30s. So I think but it's going to be a fight. It's going to be a battle. But and industries are doing this, and I've checked around with people I know in industry. They're not talking about this. Yes, IBM is talking, but the solar cell companies refuse to talk about this process. So this is pretty assured that they're all working on it. If they're all working on it, they're going to get the bugs out of it. Okay? So you have to face up to a world in which solar cells up to 30% efficient are going to be very inexpensive. And you have to draw conclusions from that. What do you do? What do you concentrate on? Where's a role for universities? What are the further implications? One of the implications that we've recognized at Berkeley, and especially at the Lawrence Berkeley Lab, is if this is true, what are we going to do with the excess electricity during the middle hours of the day? And that we should develop a process where electricity could possibly be used to make fuel in some cost-effective manner. So that's sort of the implication. Okay, so this is my final slide. These are the competing technologies. So I think the silicon is going to go down in cost. No, sir, even far below today's costs. The copper, indium, gallium diselenide, 100 startups, tremendous overinvestment by venture capitalists starting about 6-7 years ago. I don't know where they are. Their efficiency is still poor, and I don't think they have a prayer. I think it's over for them. The polycadmium telluride, that would be, as represented by First Solar, the darling of Wall Street. Yes, great achievement. They're in mass production at 11%, but where are they going? That if the rest of the world stopped, yeah, they'd be in great shape. But the rest of the world is not stopping, and they're stuck at 11%. Flat plate gallium arsenide, the one that I like. Let me say that I get very unhappy because almost every time, when I'm in the audience, somebody else is giving this talk, and they give a list of all the accepted technologies for making solar cells, and they don't even include this, which I find Well, maybe it's good. It's good. So nobody else is competing with us, but still. Okay, but they do accept gallium arsenide as useful in concentrators. And the concentrators will actually 43.5. Professor Harris here from Stanford, in his startup company, Solar Junction, has achieved that. But I have to caution you about this very high concentrator efficiency, because it throws away the 30% of the light that is not coming directly from the sun. So if you would allow me then to multiply the 43.5 by 0.7%, Alta is still the efficiency leader. Okay, because we collect that much more light. It's just there. So it's not that I'm against concentrators, but you have to be realistic that you are throwing away 30% of the light. Okay, so that's it. I welcome questions, and I'll stay behind for a few more if you like. Yeah, thank you.
This hand went up first.
For the why does the pressure point in
Okay, so this is sort of, I'll repeat the question. This is sort of an inside baseball question that people ask when they look at this table. You know, I show the table, and I'm flabbergasted that you guys can see everything on the table so easily. Here it is, here's the table. And so the question was, this was your best solar cell, and it's capable of 33.4% efficiency. And why does it have slightly less voltage with the light trapping, slightly less voltage than just a simple untextured cell? And it has to do with the subtlety. Because of the light trapping, you absorb, obviously you absorb more, and the effective band gap gets to be smaller because you absorb a little bit deeper into the infrared. And so it's kind of a subtle point, but you end up losing 20 millivolts when you do that.
So if the light is escaping from the top cells, but reabsorbed in the bottom, you don't lose and as long as you reflect it from the smallest gap back out with a back surface mirror, is that right?
Right, actually, so let me just introduce Professor Jim Harris, who's an expert on the subject, and is asking about this. So this is an idea. Actually, I had this idea only a few months ago, but it turns out Professor Martin Green of Australia already published this about 8 years ago. And the idea is that it's very difficult to current match, right? Because this is a big knock against tandem solar cells. How can you ever guarantee current matching? Different parts of the day, the sun has a different spectrum, and so forth. Okay, so this is a way of dealing with current matching, is that some percentage of the luminescence, and by the way, for high efficiency, of course, I argue you need luminescence. So some percentage of the luminescence can be emitted, and then instead of being reabsorbed in the top cell, is reabsorbed in the bottom cell. And what this means is that even if you haven't perfectly matched the currents, if you use this mechanism, you can get adaptive current matching. So I believe the future of tandem solar cells is adaptive current matching, where you arrange for there to be a little extra current in the upper cells, and what that does, you end up operating at a lower current, so the excess current goes and guarantees the current matching into the lower cell. I thought it was a very clever idea, but as I say, it's already out there. But that's good. That means that two people thought of it, and so maybe it's a good idea and it's worth working on.
So, but if the things are emitted out of the top cell and absorbed down lower, and then re-emit,
well, of course, if you do that, you give up a little bit of voltage. So you could hope from the top cell maybe to get 1.5 volts, and from the bottom cell to get 1.1 volts. And so you'd lose that 0.4 of a volt, which, okay, you can lose it, but most of them are not lost, so you do get the benefit of the higher band gap. And so this is, I think, one of the lessons. If you have an exotic idea that is not quite ready for prime time, and maybe it's lacking in efficiency and it's not quite there yet, it may have a role as an upper band gap solar cell, because what gets wasted or not absorbed in the upper cell can then be used in the lower cell. And there's this mechanism to produce current matching. So it's, I think it's kind of attractive.
You mentioned that by making a solar cell a tenth as thick, you can make it cost 10 times less. Do you believe that?
Well, the material cost would be 10 times less.
Yes.
To the extent that you believe the materials cost is important, which some people believe, and certainly they believe. Oh, yes, yes, but you have to, it's bookkeeping. So what if the material cost is actually not important? If the material cost is not important, then so why bother going to a tenth of a micron? So it's a matter of degree. If you've got all the other costs knocked down, then you have to start worrying about material cost again.
$1.50 a watt silicon module. Of that, 55 cents a watt is the wafer. So we have $1 in cost associated with taking a material bought. Let's say it's free. Now it's $1. That's a significant amount of money.
So you're pointing out one of the problems in the way silicon solar cells are made today. And that's exactly the problem they have to get away from. And that peeled film technology is the way they're going to get away from it. To the degree that they can do the peeling, no extra cost associated with the peeling, the part they paid for the silicon, that's just proportional to the thickness of the silicon. The rest is bookkeeping.
It's not though, because by making the cell a tenth as thick, I mean, you have to use a tenth less glue to do your peel, a tenth less money, health insurance of your employees, a tenth less, like your family.
It's just the material part of the cost that goes down. Obviously, the other costs are still there.
But that's a small amount, you agree?
And it depends. Some people think gallium arsenide is expensive. If you think gallium arsenide is expensive, then you'll want to take that cost out as well. In the case of silicon, it's not simply a matter of reducing the material cost. It's also balancing it off against the improvement of efficiency. The voltage goes up. There are many different factors in arriving at the optimum thickness. So I think you're pointing out that there are many different factors.
Okay, we've gone over in time.
For more, please visit us at stanford.edu.